So let's continue our discussion of Galois theory from where we left off in the previous video. So you may remember that we have already gone through the definition of solvable groups. And let us see it once more. A group G is called solvable if there exists a finite decreasing chain of subgroups like this. And it starts with the given group and ends with the trivial group, so that each Ni is normal in the previous group, because each Ni is a subgroup of the previous group in this chain. So it is normal in Ni minus 1, and the quotient of Ni minus 1 by Ni is abelian for all these i's. Alright, so let us now see some examples of solvable groups. The first thing one can note is that every abelian group is automatically solvable if G is abelian, then G is solvable. Why? Because we can have such a chain of subgroups like this, taking n naught equal to G and n1 equal to E. We see that so that means for an abelian group, this chain has only two elements. The first of which, of course, is just G, and the very next element is the last one. But we also need to see that the other conditions are true. N1 is normal in N0. Is that true? Because N1 is the trivial group, which we know is always normal in any group. That means N1 is normal in N0. And N0 slash N1, which is nothing but G slash E, and that is isomorphic to G itself, is abelian because G is abelian. And that's why if G is abelian, then G is automatically solvable. Next comes an example of a non-abelian solvable group. The symmetric group of degree 3, that is our familiar group S3, is solvable. Take N0 equal to S3, N1 equal to A3, the alternating group of degree 3, consisting of all the even permutations. And the even permutations in S3 are the identity, and other than that, the 2 3 cycles. 1 2 3 and 1 3 2, and N2 equal to E. Now we know that this subgroup of S3 is normal in S3. We already know this, and if you want to justify how, you note that this is a subgroup of S3 of index 2, and index 2 subgroups are normal, we already know. So that's how N1 is normal in N0, and N2 of course is normal in N1 because it's the trivial group. Note that N1 is normal in N0 and N2 is normal in N1. Okay. Also, N0 slash N1 and let me write together and N1 slash N2 are both abelian. Why? That's because we are dealing with finite groups, right? So let us see what the orders of these groups are. You know how many elements S3 has? 6, and N1 has 3 elements. So the order of N0 slash N1 is 2, and the order of N1 slash N2, which is isomorphic to N1, is 3. And that is why these groups are abelian, and not just that, due to them having prime orders, they are in fact cyclic. So that is why S3 is solvable. Similarly, S4 is also solvable, and this is one of the exercises. This is exercise 3. So while solving the exercises in the community section, we will see how S4 is solvable. But for all integers n greater than or equal to 5, the symmetric group Sn is not solvable, and this is in fact our aim. We will prove this fact. Not in this video itself, but we are going towards that. Is not solvable. Now we know the definition of a solvable group, but we need some other description of solvable groups. That is some necessary and sufficient condition for solvability of a group. And to have that, we need to recall something which we have already come across, namely commutators of group elements and commutator subgroup. So let's just recall that. For a group G, any group G, finite, infinite, abelian, non-abelian, we are not saying anything. For a group G and elements A and B in G, we say that A inverse B inverse AB is the commutator of A and B. Okay. We have already seen this before, not in the body of the text proper, but in one of the exercises. I think at the end of the section where we discussed homomorphism, okay, group homomorphism, at the end of that section there are exercises. So one of those exercises has this thing. The subgroup of G that is generated by the set of all commutators formed from elements of G, that is understood, is called the commutator subgroup of G and is denoted like this, G prime. Perhaps this notation will remind you of what we are talking about. We require that the subgroup generated by the set of all commutators, as opposed to simply considering the set of commutators itself, because that set is not necessarily a subgroup. But that set, of course, generates a subgroup. Do you, however, remember what is this generated by a subset means? Say, let me just talk about that briefly a little. Say you have a group G and you have a subset S of G. Now imagine the collection A whose elements are H, such that H is a subgroup of G and H has A as a subset. This collection is non-empty because G itself is an element in this collection. G is a subgroup of itself that has S as a subset. So one can consider, because this is non-empty, there is no problem in considering the intersection of all the elements in this collection. This is called the subgroup generated by the subset S. One can prove that this is a subgroup of G. We often denote this generated subgroup like this. And it turns out that this is the smallest subgroup of G which contains S as a subset. So that thing. In place of S, if you have the set of all commutators, and say the set of all commutators, let me call it C. Okay, then the subgroup that C will generate is this G prime. Okay, so that's the thing. Now C itself may not be a subgroup. That's why we take the subgroup generated by C. Now let us actually recall the exercise and the section where we came across this thing. We proved in exercise 5, section 7 of the second chapter, that means that homomorphism section, that G prime is a normal subgroup is normal in G, and because it's normal, you can consider the quotient group, and this is abelian. Okay, so this is something we have already proved in that exercise, and we are going to use this fact. But not just that only, we proved something else also. Also, if M is a normal subgroup of G such that the quotient group is abelian, then M contains the commutator subgroup inside of it as its own subgroup. These are the things we proved in this exercise. Alright, now there is no reason to stop here itself, because the subgroup G prime is after all itself also a group, so we can consider its commutator also. Since G prime is also a group, we can consider its commutator subgroup, which we denote like this: G superscript 2 within parentheses. So this is the commutator subgroup of G prime. So from the definition of commutator subgroup, we know this. Thus, G2 is the subgroup of G prime generated by elements of this form. Generated by elements means generated by the set of such elements. A prime inverse, B prime inverse, A prime, B prime, where A prime and B prime now are coming from G prime. Okay, previously in our first, just for the simple commutator subgroup, the elements come from G. So this time we are considering the commutator subgroup of G prime. So the elements whose commutator you are going to consider, they will come from G prime. Okay. Now here is something, so automatically we can apply these results here also. For example, we know that G2 is not just a subgroup of G prime, but it's a normal subgroup of G prime. And if one forms the quotient of G prime by G2, that quotient group will be abelian, which is nothing new. So we are just stating these things for the group G prime. But something else is also true. The group G2 is not just, or let me write like this, is normal in not just G prime but in G as well. Okay, so this is a fact we will have to prove, and this will be proved in exercise 4. And one can continue to form other commutator subgroups, say the commutator subgroup of G2 and then the commutator subgroup of even that. So one can continue to do so. Continuing like this, one can define G superscript n, which is the commutator subgroup of the previous group, in this way of defining things. And that previous group of course is Gm minus 1. And one can prove that actually all these groups are normal in G. And that is also, the general statement will be proved in exercise 4. Okay. So let us now look at a criterion for solvability of a group in terms of these groups, these GMs. And that is this next level. So this is going to be lemma 571. The group G is solvable if and only if the group GK is trivial for some positive integer K. Okay, so instead of looking for such a decreasing chain of subgroups satisfying those conditions in the definition of solvability, one can calculate these groups as well, this GK. One can go on calculating them. If one hits the trivial group for some K, then that would imply that G is solvable. Conversely, if G is solvable, then you go on calculating these groups, you would eventually reach the trivial group for some K in a finite number of steps, of course. So let's now see the proof. So in the proof, the author has first assumed this and shown that G is solvable and then went for the converse. Let Gk be equal to E for some positive integer K. This side of the proof is very easy, straightforward. The converse is also straightforward, but this is particularly easy. You almost do not have to do anything. So that means in this half of the proof, we have to prove that G is solvable. Take n not equal to G. See, showing that G is solvable means showing that such n i's exist, satisfying those conditions. So we will now choose those n i's. Let n not be G. N1 be the commutator subgroup of G. N2 be this. Let me write one more. N3 be this group. So like that we go, and eventually we have Nk, and let that be this Gk, which is given to be trivial. Obviously, the way we define these groups, for example, G prime is the commutator subgroup of G. So after all, it's a subgroup. G2 is the commutator subgroup of G prime. So this is a subgroup of this. So the further you go down this sequence of groups Ni, each one is a subgroup of the previous one, naturally. Clearly, so let's just write that first. Or, okay, no, this is not how we write. We write G first. So this contains N1, N1 contains N2, N2 contains N3 and so on. Finally, we have Nk, which is the trivial group. All right. Now, by exercise 5, section 2.7. So now we can use that result, because you see our Ni's are now the successive commutator subgroups. So what are we going to write? First we will write this. Let me write in detail so that it looks nice. Looks nice means it looks more clear. N1 is normal in N0 and N0 slash N1 is abelian. You just put what, you see what N0 and N1 are. N0 is what? G. N1 is what? The commutator subgroup. So by that exercise, we know that the commutator subgroup is normal, and we also know that this quotient, which is nothing but G slash G prime, is abelian. And similarly, again, by that exercise, applied now to this group, we also get this. N2 is normal in N1 and N1 slash N2 is abelian, and it will continue until we reach the last group. Nk is normal in Nk minus 1 and this quotient is abelian. So naturally G is solvable. This is 1/2. Conversely, let G be solvable. Then you apply the definition of solvability, then there exist subgroups G equal to N, okay. If you want, you can, here also you can write N0, N1 up to Nk, but because we have used the Ni's like this here, no, so let me just use some other symbol, say M1, because it's in the same proof, right? So to avoid any potential confusion, let me write something like this. And also instead of taking k, let me take say r equal to e, such that just like k, r is also some positive integer, such that mi is normal in mi minus 1 and the quotient is abelian. For all these i's. Okay. Now again we are going to take the help of our previously solved exercise by exercise 5 section 2.7. Now we are going to write some containments and I will say something about these containments. A part of these containments will be immediately clear, but something else also extra needs to be said. So the first thing is this. You see, actually now we are going to use the other part of this exercise, that part which says this, that if M is a normal subgroup of G, which is, for which this quotient group is abelian, then if this is abelian, then M contains G prime. Okay, so we are going to use this. So the first thing that we can say here in this situation is what? We know that M1 is a normal subgroup of M naught. Sorry, I should have written 0 here. Yeah, sorry about that. MR of course stays MR. So M1 is a normal subgroup of M naught, which is G. Okay, and at the same time, this is abelian. So that means M1 should contain this. Okay, so that is our first conclusion. M1 contains the commutator subgroup of G. Now you apply the same thing to M1 and M2. Here you have M1 and here you have M2. M2 is a normal subgroup of M1 because that is the condition we are getting from solvability, such that this is abelian. So M2 should contain the commutator subgroup of M1. Alright, now the commutator subgroup of M1, this much we understand. Okay, it follows immediately from this result. However, this is not enough. Next we write from this containment and this containment, we write this, which is G2. The question is, can you take commutator on both sides and still have containment like this? That's the question that we have to answer. Because if we can, then we can continue writing things like this. What will you, let me write one more. What will you get for the pair M2 and M3? 2, 3. This is what we already have, and the conclusion is that M3 contains the commutator subgroup of M2. Now M2 contains G2. So the commutator subgroup of M2 should contain the commutator subgroup of G2, which by definition is G3. Okay, so M3 contains G superscript 3. M2 contains G superscript 2. So like that one will go and eventually one will reach this. Mk contains the commutator subgroup. Hold on, I need space. Or we can directly write Mk contains Gk. Okay. So let us now answer that question. This is the question. Say you have two groups, G1 and G2, and say G1 is a subgroup of G2. Does this imply that the commutator subgroup of G1 is also a subgroup of the commutator subgroup of G2? And the answer is yes, because this is what we are using here. But how? You just imagine an element in the commutator subgroup of G1. What type of element will there be? What is the definition of the commutator subgroup of G1? It is the subgroup generated by the set of all commutators formed from elements of G1. Right? And we know there is a result which says what type of element we can expect to have in the subgroup generated by a subset. Say S is a group, G is a group and S is a subset, right? And say S is also non-empty. Then can you write the structure of the general element of that subgroup generated by S? Yes. And that element will look like this. S1 to the power R1, S2 to the power R2, say ST to the power RT, where T is a positive, now comes the condition, where T is a positive integer. These exponents are all integers. They may be positive, negative or 0, each one of them. And these bases all come from S. This is how a general element in this subgroup generated by S looks like if S is non-empty. So that's how any element in G1 prime will also look like. So a general element in G1 prime will look like this. This is not a part of the actual proof, so I have separated it. A general element in G1 prime will look like this. A1 inverse, B1 inverse, A1 B1 to the power R1 times A2 inverse, B2 inverse, A2 B2 times, and it goes like that, AT inverse, BT inverse, AT BT to the power RT, where these A1 B1, A2 B2, AT BT, these are all coming from G1, Why have we considered S to be non-empty here? Because you see, the set of commutators of elements of G1 is a non-empty set, because G1 itself is a non-empty set. That is why. But G1 is a subset of G2, so that means these elements after all are coming from G2. So just like they are commutators, I mean these are commutators in G1, these are also commutators in G2, and that is why this general element also belongs to the commutator subgroup of G2. So that's how this containment it produces another containment between commutator subgroups like this. That's why these things are justified. Okay. But now what is the consequence of this? We already know that our final MK, keep in mind that these MKs are coming from, I mean the MIs are coming from the fact that G is solvable. So the final MK is trivial. Since see, I made a mistake. This is not K, this is R. Yeah. So MR is trivial. We have GR also trivial. But that's what we wanted to show, right? For a solvable group G, if you keep on finding these commutator subgroups, after finitely many steps, you hit the trivial group. So this completes the proof. Now this result has a small corollary. Let us see that, and then we will stop for tonight. And the corollary states this: if G is a solvable group, and G bar is a homomorphic image of G, then G bar is solvable too. Okay, so any homomorphic image of a solvable group is solvable. Any isomorphic image, of course, is solvable, because isomorphic groups are group theoretically the same thing. But this is a homomorphic image. What do we mean by homomorphic image? This means that there exists a homomorphism from G onto G bar. Okay. In that sense, it's a homomorphic image, because the image is equal to G bar. Alright, and its proof is also not very difficult. It's just something which uses the previous result and a simple observation. Since G bar is a homomorphic image of G, G bar K is a homomorphic image of GK. for all positive integers k. How? Let me give you a hint. I won't say much, but because G bar is a homomorphic image of G, so there exists an onto homomorphism from G to G bar, right? And what is Gk? No matter what this k is, this Gk is after all a subgroup of G. Now using these two things, you show that this is a homomorphic image of this. The rest I leave to you. Exactly how that I leave to you. You should be able to show this. Okay, now let us use the previous result. Since G is solvable, this is equal to trivial for some positive integer k, and here we are using the previous lemma by lemma 571. Then this is also trivial. Why? Because see, whatever we are stating here ultimately means what? Ultimately it means that there exists a homomorphism G from Gk onto G bar k. And so if, and what does that mean in turn? It means that the G image of Gk is equal to G bar k. Now if this is trivial, then this also has to be trivial because of the existence of such an onto mapping. And that's why we have this. But then, by again this lemma which works both ways, (571), this is also solvable. This result can be proved without the use of this lemma also, but it will involve some effort, okay. It won't come out this easily. But anyway, we now have the proof. And let me just stop here itself. In the next video, we are going to consider these groups, where Sn is the symmetric group of degree n and n is at least 5. We will prove that no matter what this positive integer k is, any such group contains all the 3 cycles of Sn. And this result will take us towards that claim that all these groups Sn, where n is at least 5, are non-solvable. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.